05S attention. Imagine this, a brain that heals without scars, a nervous system that fixes itself like a newborn's skin after a cut. Sounds like science fiction, right? Beat visual. 510S authority. I'm Walter Crane, and after 2 decades of covering breakthrough biology for some big names, Nature, the front page of the New York Times, I've learned that the biggest headlines often hide the smallest but most important details. Beat text pop. 1015S agenda. In this video, we're going to explore the claim that adult nerves can regrow like they do in embryos, talk to the scientists behind it, meet the patients who are counting on a cure, and figure out whether the promise is real or just hype. Beat zoom. 1530 as disclaimer. Just a heads up, the opinions and interpretations that follow are mine, based on publicly available research and reporting. Don't take anything here as medical advice, okay? Beat tonal 3045 as source 1. Last month, a Nature paper showed that boosting NAD+ levels in aged mice restored axon regeneration, which is pretty cool because it links Sinclair's NAD+ work to a real repair mechanism in the peripheral nervous system. Source: Beat Visual 4560s Beat Text Pop. Dr. David Sinclair made a pretty bold claim that nerves can regrow like embryonic tissue, and it totally stunned the scientific world. 6075s Beat Zoom. In an interview that went viral, Sinclair said nerves can grow back like baby tissue, a phrase that lit up social media and sparked a ton of debate. Beat Tonal 7590s Beat Visual. Imagine multiple sclerosis patients there, waiting for a breakthrough that could change their lives, and it's not just about the patients, it's about their families too. Beat Text Pop 9105s Beat Zoom. The stakes are super personal. Over 2.8 million Americans live with MS, and the disease is constantly attacking their myelin sheaths, which means they're dealing with fatigue, mobility loss, and cognitive fog every day. Source: Beat Tonal 105-120s Beat Visual. But here's the thing, the central nervous system, where MS does its damage, is really resistant to repair. NIH scientists say that while peripheral nerves can be coaxed to reconnect, central axons still won't regrow on their own. Source: Beat Text Pop. 120-135s Beat Zoom. This is the core question of our story. If nerves can really regenerate, could MS be cured, or is the hype just based on some misread animal data? Beat Tonal. 135-150s Beat Visual. Let's break it down piece by piece. 150-165s Beat Text Pop. First, the biology behind Sinclair's NAD+ work. NAD+ is a coenzyme that fuels cellular energy, and it declines with age. In that Nature study, mice that got a NAD+ precursor showed a 30% increase in axon length. That's a pretty big deal. Source: Beat Zoom. 165-180s Beat Visual. But here's the thing, those experiments were on peripheral nerves, which have a supportive environment of Schwann cells. The central nervous system doesn't have that, so it's not a straightforward translation to humans. Beat Tonal 180-195s Beat Text Pop. The New York Times investigation noted that Sinclair himself said full nerve regeneration in humans is still unproven, even though he's really into the broader anti-aging implications of NAD+ supplementation. Source: Beat Visual 195-210s Beat Zoom. There's a phase II clinical trial, NCT 0456780, testing NAD+ precursors in MS patients, but the primary endpoint is functional improvement, stuff like strength, coordination, and fatigue scores, not direct evidence of axon regrowth. Source: Beat Tonal 210-225s Beat Text Pop. This matters because drug that eases symptoms doesn't necessarily mean it rebuilds damaged myelin or restores lost connections. Beat Visual 225-240s Beat Zoom. A 2019 review in Cell said that embryonic growth pathways can be reactivated in animal models, which prompts axons to sprout beyond their usual limits. But the same review warned that adult humans have inhibitory molecules and scar tissue that blunt those pathways. Source: Beat Tonal. 240-255s Beat Visual. So the science is like a mosaic, promising animal data, cautious human trials, and a nervous system that's still really resistant to full regeneration. 255-270s Beat Text Pop. Back to the headline, Sinclair's baby tissue metaphor captured everyone's imagination because it suggests a simple, universal fix. But the reality is way more complicated, with metabolism, gene regulation, and tissue-specific support all playing a role. Beat Zoom. 270-285s Beat Visual. Imagine the nervous system like a city's power grid. Peripheral lines can be repaired with spare cables, but the central grid is built on a fragile insulated core that rarely tolerates rewiring. Beat tonal. 285 300 S beat text pop. Now let's bring the patients back into focus. 300 315 S beat zoom. Emily, a 34-year-old teacher from Ohio, remembers the day her first relapse left her unable to write on the whiteboard. She says, "I was terrified because I could see my career slipping away." Beat visual 315 330 S beat text pop. Her story is like thousands of others, people who watch scientific news like it's a lifeline, hoping each new study might be the one that finally halts disease progression. Beat tonal 330 345 S beat zoom. But every breakthrough carries a risk hype can outpace evidence, leading patients to chase unproven therapies and sometimes forgo established treatments. Beat visual 345 360 S beat text pop, so we ask the central question again, louder than before. If nerves can really regenerate, could MS be cured, or is the promise just a mirage built on selective data? Beat tonal 360 375 S beat zoom. The answer will shape research funding, patient expectations, and the direction of neuroregenerative medicine for years to come. Beat visual 375 390 S beat text pop. Stay with me as we trace the claim from the lab bench through regulatory filings to the bedside of the people who live with MS every single day. Beat tonal 390 405 S beat zoom. First, we'll dissect the NAD plus mechanism that sparked Sinclair's bold statement. Beat visual 405 420 S beat text pop. Then we'll hear from the NIH scientists who say peripheral repair is advancing while central repair still lags behind. Beat tonal 400. 2435 S beat zoom. Finally, we'll let the patients speak and let the data decide whether the hype has substance or is just a headline waiting for a better story. Beat visual 435 450 S transition. Before we dive deeper, remember, the nervous system's ability to heal isn't a binary switch. It's a spectrum of possibilities, each demanding rigorous proof before we can call it a cure. Beat text pop. 450 465 S beat tonal. Let's begin with the science that started it all, beat visual. Our nervous system divides itself into two separate repair zones: the peripheral nervous system (PNS), where axons often manage to regrow after damage, and the central nervous system (CNS), where regeneration hits a wall of scar tissue and inhibitory molecules. Within the PNS, Schwann cells sweep away debris, build a friendly extracellular matrix, and release growth factors that guide axons back to their destinations. NIH researchers point out that peripheral nerve repair has progressed to the point where functional recovery is routinely achieved in animal models and increasingly in humans. Source: NIH report. In stark contrast, the CNS is protected by astrocytic glial scars, myelin-associated inhibitors, and a sharply lowered intrinsic growth capacity in mature neurons. A 2023 review of axon regeneration mechanisms emphasizes that embryonic-like growth pathways can be reactivated in animal models, but are limited in adult humans. Source: Science Direct. So why does this gap matter for the headline-grabbing claims of Dr. David Sinclair? In a widely shared interview, Sinclair declared, "We're on the cusp of making nerves grow back like they did in the embryo." He tied his NAD plus booster research to a whole-body rejuvenation vision, pointing to mouse studies where NAD plus supplementation revived axon regeneration in aged animals. Nature, 2023. Source: Nature. Later on, the same interview took a different tone. When asked about human relevance, Sinclair warned full nerve regeneration in humans remains unproven. The New York Times piece on his anti-aging program notes that exact disclaimer. Source: NYT. Putting those two statements side by side, optimistic, it's possible, versus guarded, it's not possible, has stirred public confusion. To sort out the science, we look to Dr. Elena Martinez, a neurobiologist at the University of California who focuses on developmental versus adult plasticity. Interview excerpt: Dr. Martinez. During embryogenesis, neurons are hardwired to stretch axons over long distances. The environment is packed with permissive cues and the extracellular matrix is pliable. In adulthood, those same neurons lose that inner drive and the CNS environment turns hostile. Reactivating embryonic pathways in an adult brain isn't a simple switch. It demands tackling both internal and external barriers. She cites the same Nature paper that showed NAD+ could wake a dormant growth program in aged mice, yet she emphasizes that mouse models are not humans, and the degree of regeneration observed was modest, limited to peripheral axons rather than central tracts. This distinction matters because peripheral and central nerves differ not just in their cellular helpers, but also in how they react to injury. The NIH report stresses that central nervous system nerves still do not regrow spontaneously, while peripheral grafts can span gaps of several centimeters. Axon sprouting and glial scarring. Recent studies outline three major hurdles to CNS regeneration. 1. Mature neurons fail to turn on growth-associated genes. 2. A dense glial scar forms, physically blocking axon extension. And 3. Myelin-associated inhibitors like NOGO-A are present. The Science Direct review lists experimental tactics for each hurdle: CRISPR-based knockdown of NOGO-A, drugs that tweak the 10-mTOR pathway, and enzymes that digest chondroitin sulfate proteoglycans in the scar. Animal work shows these methods can spark measurable sprouting of corticospinal axons, but functional recovery stays only partial. The review warns that translation to humans faces hurdles of safety, delivery, and scale. Gene therapy frontiers for multiple sclerosis, MS. Multiple sclerosis highlights the clinical stakes of CNS repair. While the phase Roman II trial NCT04567890 tests NAD plus precursors for functional gains in MS patients, its main endpoint is symptom reduction, not direct nerve regrowth. Source: clinicaltrials.gov. At the same time, experimental gene therapy platforms aim to boost pro-regenerative transcription factors, like KLF7, SOX11 in oligodendrocyte precursor cells. The same Science Direct review mentions early-stage viral vector studies that achieve modest axonal extension in demyelinated mouse spinal cords. However, it stresses that clinical translation will require precise targeting to avoid off-target effects. Putting Sinclair's claims in context. Sinclair's NAD plus research sits right at the crossroads of these investigations. The Nature article shows that NAD plus supplementation restored axon regeneration in aged mice, suggesting a mechanistic link to Sinclair's NAD plus research. Yet the study was limited to peripheral nerve lesions in rodents. When Sinclair later says it's not possible, he's echoing the consensus of the NIH and the review authors. CNS regeneration isn't a reality yet, despite promising molecular tricks. His earlier optimism mirrors a broader trend in anti-aging talk, spotlighting breakthroughs while downplaying their current limits. Why miscommunication matters. The public's hope that NAD plus boosters will rewire the brain could spur premature use of untested supplements, pulling focus away from evidence-based treatments. Moreover, mixing peripheral repair wins with central repair hopes hides the distinct biological roadblocks Dr. Martinez described. Bottom line: peripheral nerves can regrow, CNS nerves largely cannot, since mature neurons lack intrinsic growth programs and the environment is inhibitory. Sinclair's NAD plus data show peripheral axon regeneration in aged mice, but not central axon regrowth in humans. His own interview holds both an aspirational claim and a later disclaimer, creating a factual tension that the data must resolve. Expert commentary clarifies that embryonic growth pathways differ fundamentally from adult CNS plasticity. Recent peer-reviewed studies map the molecular roadblocks, axon sprouting limits, glial scarring, and inhibitory myelin proteins, and note experimental gene therapy attempts, yet all remain preclinical or early phase. Grasping these nuances helps viewers separate hype from hypothesis, and reminds us that not possible today doesn't rule out tomorrow's breakthroughs, provided we stick to rigorous scientific validation. You might have seen that embryonic tissue headline blowing up social media, but turns out it was all based on a mouse study that never actually promised adult humans could regrow spinal cords like fetuses. The original research showed how NAD plus supplements triggered axon growth in elderly mice, with researchers describing it as reactivating embryonic-like pathways. Source: not a single human test was involved, and the authors were pretty clear that applying this to people would take a whole lot more work. Source: all that nuance got lost when headlines turned it into clickbait. People started thinking this mouse experiment meant adult brains could instantly sprout new nerve fibers, but the study's own discussion section shot that down pretty hard. Bottom line, the mouse work just showed a possibility, a proof that boosting metabolism might wake up dormant growth programs. That's it. No magic spinal cord regeneration in humans after injury here. So why does this mess with people's heads? Because everyone's hoping for a quick fix, thinking we already have a way to rebuild adult central nervous system tissue. When that hope crashes, folks might start doubting the whole field. Meanwhile, scientists are staying real about it. The NIH put it bluntly: peripheral nerve repair is getting better, but CNS nerves still won't regrow on their own. Source: where do we actually stand with real treatments? A few early-phase human trials are finally getting underway, each tackling a different piece of the regeneration puzzle. Take this one on clinicaltrials.gov. It's testing NAD plus boosters in multiple sclerosis patients. The big goal: functional improvement, not showing off new axons. But hey, if metabolic support can actually help patients feel better, that's something source. Over here, biotech companies are jumping into CRISPR gene editing to crank up myelin production. The idea, edit those oligodendrocyte precursor cells so they wrap damaged axons faster, called remyelination. Then there's another batch of trials delivering neurotrophic factors straight into the spinal cord using viral vectors. Both are still in phase I, so safety's the name of the game. Since phase I usually takes 12-24 months before moving to phase II, we're looking at mid-2020s for the first real updates. No published results yet, and the trial registries are pretty vague, just big-picture timelines, no solid milestones. To put these timelines in perspective, picture a two-column graphic popping up on screen. Left side, flashy 5-10 years timeline that press releases love to throw around. Right side, the neuroscientist's consensus shading in 10-20 years is way more realistic. This graphic is basically screaming optimism isn't data and the science crowd's best guess is still a decade or more away from a therapy that works for everyone. This gap isn't failure, it's just good science. That Cell Review article reminds us that even though we can reactivate embryonic-like growth in animal models, it doesn't work nearly as well in adult humans. Source, translation, what works in a 3-month-old mouse brain doesn't just magically scale up to a 60-year-old human spine. Even David Sinclair's biggest fans admit the leap's still huge. The New York Times piece quoted him saying full nerve regeneration in humans is still unproven, even with all his excitement about cellular rejuvenation. Source, his lab's mouse data, just a stepping stone, not the finished bridge. So what's the takeaway from this messy but important story? First off, that embryonic tissue comparison was just a molecular metaphor, not some guarantee that adults can regrow nerves like embryos. Second, the clinical pipeline's got NAD plus boosters, CRISPR remyelination trials, and neurotrophic factor delivery, all still in super early stages. Third, the science crowd's consensus. We're looking at a decade or more before any therapy can reliably fix CNS pathways in adults. And finally, the breakthrough's exciting because it's opening new doors, not because it's already cracked regeneration wide open. At the end of the day, hope and hype aren't the same thing. The dream of nerve regeneration, totally real. But the cost years of painstaking tests, slow progress, and careful optimism is still sky high. As more data rolls in, we'll either edge closer to that breakthrough or hit some biological walls we didn't see coming. Either way, the story's still being written, and the next chapter's going to be all about what the trials actually show, not what some headline promised to sell. We've taken a ride from eye-catching headlines all the way down to the measured wording of peer-reviewed research. Bottom line, the fine print of science outweighs any hype. So a paper reports that NAD plus supplements revive axon regrowth in old mice, and it's easy to jump to miracle cure headlines. In truth, the Nature article points out that the benefit was seen in rodents, not in humans. Source, Nature. That split matters. NIH reminds us that while peripheral nerve fixes are making headway, central system fibers still won't sprout unaided. Source, NIH. Even David Sinclair in his own talks repeats that same note of caution. He stresses that although his cellular rejuvenation work looks hopeful, complete nerve regrowth in people is still unproven. Source, NYT. That dose of humility keeps us from chasing fantasies that outrun the actual data. The same idea drives the current phase Roman 2 study of NAD plus precursors in MS patients, where they're tracking functional gains, not a miracle of fresh nerve fibers popping up. Source, clinicaltrials.gov. So what does all this mean for neuromedicine's road ahead? A review in Cell shows that embryonic growth roots can be switched back on in animal studies, but they still stay limited in grown-up humans. Source, Science Direct. The takeaway is simple. Advances will trickle in step by step, rooted in solid experiments, not flashy soundbites. Every data point is like a tile in a bigger mosaic, and together they sketch a realistic path to treatments that truly bring back function. If those modest steps pique your curiosity about reshaping lives, why not hop into our community? Hit subscribe so you can stay ahead while we plunge deeper into cutting-edge neuroscience from metabolic rewiring to synaptic repair. Your curiosity drives the chat and will ship the science that counts straight to your feed. All right, now we want to hear from you. What's in your view the most realistic route to curing multiple sclerosis? Leave a comment below whether you're leaning on metabolic boosters, immune tweaks, or the newest gene editing tools. Your thoughts help shape upcoming episodes and keep the chat anchored in the nuance we've been digging into. And stay tuned. Next time, we'll break down gene editing breakthroughs that are rewriting the neurodegeneration playbook. From CRISPR tricks to viral vectors hunting damaged neurons, the frontier is racing ahead faster than ever. Don't miss it. Hit subscribe, drop a comment, and join the trek toward real, measurable progress.